Okay, precipitation reactions, which are a type of double replacement. Acid-base, also a type of double replacement, okay? And then, so basically a precipitation reaction is a precipitate is formed, okay? And then you can, if you're doing this in a lab, which we will try to do this, it's called a gravimetric lab analysis, and that's because it's using gravity to help you filter the solid. That's why it's called, it's a fancy way of saying filter something. It sounds fancy to say gravimetric analysis, but it's just using the power of gravity to pull the liquid out from the solid. So we will try to get to one of those labs because they like to ask questions on that kind. But when we're talking about precipitation, that means you have to remember your solubility rules. They're rearing their ugly head again. Specifically in AP Chem, they are only going to test over the first two. Those are the only ones you really have to know. And I believe in Chem 1, I kind of told you that too. If you learn what is always soluble, you're pretty much covered on everything. Okay? Because again, like I told you yesterday for single replacement, they're not going to give you a no reaction if they're giving you an equation in AP. It's an equation that happens because if they give you a no reaction, they can't ask any follow-up questions. No. So most nitrates are always soluble. Alkali, which is group 1, and ammonia. I would add in their acetates, but they may not put that on their acetates. Are always soluble as well. But your group 1 salts, okay, lithium on down they're always soluble. Okay. 3, 4, and 5, those are just good to know, especially the chlorides, bromides, and iodides are always soluble unless there was silver, lead, or mercury. Okay, but those are things that are just good to know. But the only ones that are directly tested on are rule 1 and 2. But I usually test you on more. I'd rather work harder in class and then the AP exam you're like, oh, that wasn't so bad, that was easy.
So what does most mean? Are there exceptions that we need to remember?
I don't know why they're saying most, honestly, because that's the solubility rules that they put out, because I've never seen any nitrates that are not soluble. I've never seen any group 1 or any ammonia.
So all of those should be all.
I think so, but this is what they put out, so I mean, I think they just hesitate to say always because there might be that one obscure thing, but I've never run across one. And then when we're talking about these later on, those things that are always soluble like that are going to always be spectator ions when we're doing things later on, especially when we get to solubility equilibrium. Those are always going to be spectators, so we're going to ignore them for the most part when we're doing things, unless they ask a question specifically like calculate their concentration at the end of the reaction. For the precipitation reactions, for this type of double replacement, the one thing that we need to remember is it's not just if it forms a precipitate does the reaction happen. If it forms a gas or a molecular compound, they also happen. And so in the case of this one here, you've got hydrochloric acid and potassium sulfite, and they form the gas of SO2 and H2O. So that would be a reaction that happens. It wouldn't be a no reaction. I don't want you to look at that and say, oh, there's nothing that's solid, so that reaction doesn't happen. If it's forming a liquid or a gas, it's a reaction that still happens, okay? And you can still write a net ionic, okay? All right. In the case of the bottom one, sodium hydroxide and ammonia chloride, you're forming the NH3 and then liquid water, okay? Next page. And there's one of a molecular substance, okay? Forming liquid water. It should have an L behind the H2O. So that would be also happening. So we're going to use the solubility rules to predict what will happen when the following pairs are mixed. Would anything happen in the first one? Well, it would form potassium nitrate, right? Plus, potassium chloride plus barium nitrate. Those are all soluble, so that one would be a no reaction. I'm just getting y'all to look at your solubility rules here. Okay. Sodium sulfate and lead 2 nitrate. Would those form anything? That would also be, no, lead sulfate would form. Yeah, PbSO4 would be your solid. That would form your solid. Everything else would be soluble. So that would, and then the last one? it would form potassium nitrate, which is always soluble because that's a group 1 and a nitrate, but the solid would be FeOH3, and that would form the solid. So those would be the things that it would form as a precipitate. Okay? And the more you work with the solubility rules, the more you get familiar with them. Okay, do you remember net ionics? It's where you have to break everything apart and just put what happens. Okay, so used to be on the AP exam, that was question 4. I loved it because my kids would knock it out of the park. Like they would usually get like 9 out of 10, 8 out of 10 points on that. They took that section away and it made me mad because we would take weekly net ionic quizzes and they could hit that one out of the park. Now they took that away. They build those into other questions. Okay, so you have to still know how to write net ionics, but it's going to be indirectly tested again. Okay, but basically you write the complete equation, break apart anything that's aqueous, and then see what appears the same on both sides, and then mark those out, and then what's left is your net ionic. You will get to the point where you can just write your net ionic without having to write the complete and the molecular equation. If you can't, that's fine. You can always write out the thing. So first of all, we're going to do this one, KOH plus FeNO3. So the complete balanced equation would be KOH, right, plus FeNO3 would yield KNO3 plus FeOH3, right? Now we need to balance that, so how do we do it? 3 and 3, right? So now the next step is to break, that's the molecular, balanced molecular equation. The complete net ionic, I would break them apart. K plus 3OH minus plus Fe3 plus 3 nitrates. And then over here that would be 3K plus 3 nitrates plus, that's a solid, so it stays together. Now what appears the same on both sides of the equation? K, 3, so that my final net ionic is 3OH plus Fe3 plus yields FeOH3 solid. They're not real big on having to write the S's and the AQs and all that, as long as they understand what you're doing. So when I look at this and I do it, I skip all of that stuff and I say, what's going to make my solid? And then I do the 2 ions that are going to make my solid. It's just faster and easier that way. But if you, when you're doing this, need to write it all out, feel free. Because, I've been doing this just a tiny bit longer. Okay? Does anybody have any questions on what I did there and why I did it? Excellent. Oh, sorry. I have to rewrite the whole thing. Do you want the final net ionic?
Yes.
Okay.
It's 3OH minus plus Fe.
3 plus
3 plus.
yields.
Yields FeO.
Yeah. Oh, I think, did I say exercise 9? I don't even know what it is. I don't have my notes in front of me. What was exercise 9? Where are you, exercise 9? It was probably going to be a work on your own, but we can do it. We'll do one of them. So aqueous potassium chloride, KCl, plus aqueous silver nitrate, AgNO3. Do you want to do the whole thing or just try to go straight to the net ionic?
Whole thing.
Okay. All right, so what is it going to make? Remember, outside, inside goes together. Do y'all remember that from Chem 1? We do the outside things together and the inside things together. That's what it's going to make, okay, for double replacement. So it's going to make Kg, not Kg, I'm just making that up. It helps to put the glasses on. I forget that I need those sometimes. So it's going to make potassium nitrate and AgCl, which is going to be my solid, right? Because chlorides are always soluble unless they're with silver, mercury, or lead. So the other things are aqueous, so if I break it apart, I'm going to have everything's 1 to 1. We like those, easy balancing. So I would say K plus, did you just dump out?
I did not fall, don't worry.
It's okay, it's the chairs. If you really want to know why it does that, go ask Mr. McGowan, he'll tell you why it dumps you out of the chairs. Because I said something about that, because he got those chairs and I warned him, I said, tell your kids not to sit on the edge, because they'll dump them out. And he goes, well, do you want to know why? Not really, Mr. McGowan, but okay. It made sense, though. But it's, yeah. Now Mr. McGowan's on my video. So I'll let him go watch it. Okay, what appears the same on both sides? The K and the NO3, so mark out, mark out, mark out, mark out. So then our net ionic would be Ag plus Cl minus yields AgCl. Pretty good? Okay. Now let's talk about precipitation reactions. This is where you're going to form a solid, filter it, dry it to a constant mass, and then use stoichiometry to determine that. I wanted to stop and make a little note about where it says dry to constant mass. You're always going to heat it twice. Okay? If they ask you a question about gravimetric analysis, you're going to filter it, you're going to dry it, and then wait, and then you're going to mass it out again, and then you're going to dry it again, and then you're going to mass it out again. The reason you do that is you want to ensure that you dried all the water out, okay? And you're going to use and if it's not consistent, then you'll dry it again, okay? Until you get 2 constant masses, okay? Because if you have too much water left in your filter, it's going to show that you had more product than you had, and it'll screw up your calculations. So that drying to constant mass means you're going to dry it at least twice, and if they don't match, you dry it a 3rd time, okay? So that's an important thing to remember, okay? All right, so here we have, calculate the mass of solid NaCl that must be added to 1.5 liters to precipitate all of the potassium in the form of AgCl, okay? So we want to figure out how much, I want to get out all of my silver, so how much sodium chloride do I need to add? This is fun. Y'all are making faces. Don't make faces, it's fun. Okay, so what did I tell you? Always remember, never forget. Volume times molarity gives you moles. Okay, so we're going to do 1.5 liters. I'll use the grid since it freaked y'all out yesterday.
That was 7th period.
No, it was y'all.
That was 7th period that you were yelling at, though.
I didn't yell at 7th period. I just went ahead and did the grid for them. And then, right? So if we just did this a while ago, we know what our net ionic is, right? Ag plus Cl minus yields AgCl. Only because we just did that one, right? We just showed that, okay? So if I look at my net ionic, I see for every 1 mole of AgNO3, right? I have 1 mole of Ag. Yes? You agree with that? And then for every 1 mole of Ag plus, I need 1 mole of Cl minus, right? Yeah, I'm running out of room, so I'm going to come down here. I'm going to squeeze it in here. For every 1 mole of Cl minus, I need 1 mole of NaCl. Yes? And then my last step, which I am completely out of room because I wrote too big, is to do what? Molar mass of sodium chloride. 58 point, I'm just going to do this down here. This is down here. 58.44 grams per mole. Hopefully you had room to put it all in one line. So, calculate that. Crossing out the units. I'll try to write smaller next time, sorry. And that gives me 8.77 grams of sodium chloride. Yes?
What's the mass for it?
That's sodium chloride. I just ran out of room. That's why I just moved that down there.
So that's your answer? That's it?
hmm So if I wanted to get all the silver out of that amount of silver nitrate, I would add that much sodium chloride and it would precipitate out all of that. Okay? Does that make sense? Sorry, I ran out of room. Okay. I think we should do another one. What do y'all think? Okay. Before I go to the next slide, does everybody have this written down? Okay. I don't have exercise 11 in here, but I'll do it. So I'll just make a new page for me. So exercise 11 in your notes, right? You have that. It says we have some sodium sulfate and some lead nitrate. And it even tells you what it's going to precipitate. That makes life easier, right? So we know that it's going to precipitate out the lead sulfate. Uh-oh, they gave you information about both. So what does that mean?
Limiting reaction.
Mm-hmm.
There's not enough room.
There is down at the bottom of your page, though. Yeah, there's down at the bottom of the page. Okay, so we're going to start. This one's going to require me to sit down so I can concentrate. I can't stand to do this one. I'm going to take more. So we're going to have 1.25. Forgot to say I was going to write. What is going on? I'm telling you, my thing is going banana brains. That is a technical term. 1.25 liters. I just want to do the time sign, and y'all are... When I do this, I don't usually do that. 0.500 moles per liter of the lead nitrate, lead 2 nitrate.
It's 0.05.
So it is, and I have it on my paper as 0.05. There we go. All right. And then if I look at my... Oh, I didn't balance the equation. So y'all balance the equation real quick. Sorry. I had it written up at the top, and I didn't see that written up. Should be, if I start with sodium sulfate, 1, 1, 1, and then it makes 2 sodium nitrates. Is that what y'all get? Okay, perfect. And we don't really care because we're not doing anything with sodium nitrate. So for every 1 mole of the lead 2 nitrate, I can produce 1 mole of lead 2 sulfate. And then the molar mass is 303.27. And that will give me 19.0 grams when I calculate that out. And now I'll just do the same thing. Basically, these are still regular stoichiometry, but instead of starting with a mass and dividing by a molar mass, we're going to do volume times molarity and then go straight into the mole ratio. So it's really not that much harder. Well, this part's not. Yeah. So this one has 2 liters of 0.025 molar sodium sulfate. It's also a 1-to-1 ratio. And that one gives me 15.2. So my answer would be 15.2 grams of lead 2 sulfate would be formed. Okay? Now, your homework's a lot trickier than this, the precipitation reaction. Okay? You're going to have to do calculating like how much leftover stuff is left over, so I want to see what y'all do with that. The answers are listed at the bottom. You're probably going to have some questions. Tomorrow is a work day. Let me stop the video and then I'll answer your question.